Example 5. Consider those vectors. We want to find the area of the parallelogram. So remember that our cross product, the length of our cross product finds the area of our parallelogram. So we can write that out, that our area is going to be the magnitude of vector A cross product with vector B. If I want to find out what A cross B is going to equal, well, A is -6, 3, 4, and B is 9, 1, -1. Whew. Could have been a scarier question if it was 9, 1, 1. So this is where I'm going to use the technique that I introduced to you guys the other day, where highlight the first row, cross product, so -3 minus 4, -7. Highlight the second row, 6 minus 36, -30. And the second one you make negative of whatever you have. So it becomes +30. And the third one, -6 minus 27 will be -33. Well, that is the cross product. To figure out the area of the parallelogram, we need to find the magnitude of A cross B, which will just be 7 squared is 49, plus 900, plus 33 squared. I know I'm 1089. There we go. Now I have it memorized. And add those all up and take the square root. So, square root of...
Can we make it non-calculator?
Make it non-calculator? Yes, I'd like this non-calculator to 3 decimal places. There you go. Good luck. That should take you to the end of the semester. Well, yeah, it's doable. I showed you how to do the square roots by hand, so you should be fine. Now, part B to this, well, it's not really listed as part B, but it's part of the question, says, once you've found the area of the parallelogram, find the angle between those two vectors. So now we have 2 different ways of finding the angle between 2 vectors. Because our cross product, if we use length of u, length of v, sine theta times the unit vector, would be one way. And our dot product provides us another way. We'll do the dot product because it's better, and I'll explain why it's better in a second. We'll do the cross product after and show why there's a problem with the cross product in solving for the angle. So the dot product says that cos of theta is equal to the dot product over the length of A times the length of B. A little dot for multiplying. Okay? So our cross product here, our dot product, multiply the corresponding elements, -54 plus 3, -51, minus 4, -55. And the length of A, I should just have my paper so I don't have to keep scrolling up. The length of A will be 36 plus 9 plus 16. (61). And the length of B will be 81 plus 1 plus 1, root 83. Okay? And at this point, we could do cos inverse of that fraction. Now notice that cos is negative. What does that tell us? It's in quadrant 2 and 3, but we're finding an angle between two vectors, so it's either going to be obtuse or acute. And so it'll be in quadrant 2. And if it's in quadrant 2 and you go to your calculator, you can just do cos inverse of negative 55 divided by the square root of 61 times 83. You know it's in quadrant 2 because cos is negative. Because if you're figuring out the angle between two vectors, okay, if it's obtuse like this, this is the angle you're finding. Here's your quadrant 3 angle that corresponds to it. But technically when you're saying, well, what's the angle between two things, you're talking about the non-reflex angle. A reflex angle is when you have an angle bigger than 180. But I don't know what the word for an angle less than 180 is, because we have obtuse and acute. So I used unreflex. Maybe it's dereflex. Dereflex. Or you can pronounce like dereflect. Isn't that an actual word? I don't know. I don't know. My mind is, Deflect. There you go. Defect is also a word, but I use that to describe myself sometimes. Okay.
Opposite of reflecting.
Oh, we're going to find it out.
What's the diagram? Just 140.
The diagram is to show that this is your 140 for your angle theta, whereas he says, why is it not in quadrant 3? Well, technically, this is your quadrant 3, the bigger one, but when you're finding the angle between two vectors, you're either going to find an acute angle or an obtuse angle, not the bigger angle along the outside. Okay? Now, if you chose to find this out by using sine theta, I'll use A and B, is the cross product of A and B divided by length of A, length of B. And technically at this point, because you're solving for sine of theta and wanting a number, okay, we're going to just do the magnitude of A cross B. So the magnitude of A cross B we figured out, right? We figured that out to be 45.144 divided by square root of 61 times square root of 83. So let's see what happens when we take this answer, which is, I might actually, just so that I can use exact values, this was 2038. Okay? So I'm going to go to sine inverse now and do sine inverse of that square root of 2038 divided by the square root of 61 times 83. And I get 39.4 degrees, because sine is positive, it could be in quadrant 1, or sine is positive in quadrant 2 as well, or 140.6 degrees. So the problem with the cross product is now we don't know which one it is, whether or not it's the acute angle or the obtuse one. The dot product is better for this reason. So if I did decide to use the cross product and I got this, I might use the dot product just to find out that it's negative. And when the dot product is negative, your angle is obtuse. When the dot product is positive, your angle's acute.
So, I missed the notes, so I don't know. Can you do cross product with cos as well, or is that
No, the beginning of the cross product says that A cross B is equal to the length of A, length of B, sine of theta, times by a unit vector perpendicular to both A and B, following the right-hand rule, or the toothpaste rule, which I think is easier to remember. Perfect. So some properties of the cross product. Okay, we've seen, yes?
It's sometimes called a convex angle. But that's
Convex.
like there's no with
Yes.
O.
There's no. So you've got convex as in all the angles in a hexagon are convex. Okay. Awesome. I like it. Oh, we're on properties. So our properties, we've seen that the cross product in one direction is the negative of the cross product in the other direction, because one would be pointing upwards or outwards, and one would be pointed downwards or inwards. The cross product can be distributed, but we've seen how much work the cross product is, and we've seen how much work adding vectors is. Why would you want to do more cross products when you could just add them together? But if you wanted to, you could. Okay? And it works in both ways there. If u cross v is equal to 0, I don't know how the numbers here are kind of messed up a little bit. I'll have to look at that. And u and v are not 0 vectors. So if you get your cross product to be 0, your two vectors are parallel. So that is a nice little property. And if they're parallel, okay, if they're parallel, then the cross product is 0. Now this is something in logic here. What we see in number 4, number 5 is something mathematically that comes up in logic. It's not always the case that if one thing implies something, that something else implies the opposite. But it is true in this case. If the cross product's 0, you know they're parallel. If they're parallel, you know the cross product's 0. Both ways tell you something. I'm trying to think of a good example where, here, this is a great example. All horses have 4 legs. The opposite of that, all 4-legged things are not horses. Right? In one way, the statement is always true, but in the other way, the statement isn't always true. So that's a logic, something you would study if you studied logic. In this case, it's true in both directions. If the cross product's 0, you know they're parallel. If they're parallel, you know the cross product is 0. And if you have some constant with the cross product, you could multiply that constant after, or you can multiply it in with either vector to begin with. But not both, right? It's not, because it's sort of like multiplication. Similar to if I have 2 times 3 times 4, I could choose to do 12 times 2 and get 24. I could choose to do 6 times 4 and get 24, or I could choose to do 8 times 3 and get 24. I cannot choose to do 6 times 8 and get 24. Right? That would be bad. You could get 48 and then just divide it by 2 because you screwed up, yes. But we do not distribute when multiplying. Okay. Second last application. Consider these vectors. Use the cross product to show that they're parallel. So here's our first vector, cross product with our second vector. What was the way that we showed they were parallel before this? There would be some constant. Can you see that if you multiplied vector A by a -2, it equals vector B? I still think that is the best way to show that two things are parallel, to show that one is a scalar multiple of the other. But with the cross product, again, we'll use this. Do you like this technique? Are you easy to visualize? Okay. -2 minus a -4, 0. Okay. 6 minus 6, -0. And 12 minus 12, 0. Okay? And yes, you don't need that negative there. But it does make the 0 vector. And because of that, yeah. Since the cross product is equal to the 0 vector, we know that these two vectors are parallel. Yeah.
Okay, wait. I have one question.
Because otherwise it doesn't, like, why did you do that?
How are you showing that these vectors are parallel? And, like, I could just, like, could we just show that?
Using the property, all right, if you want to,
Where, like, you're just putting what they gave you and just saying that you can do it.
He means like with this strategy of how we do it.
Yeah, how do you
Since we know it has to be 0, we can do no
Just
work.
write zero,
Just
zero,
zeros
zero.
in.
Well, it's showing that it's cross. I think you have to actually cross.
yeah, I guess you're,
Exactly. Like he's like, you
y- y-
question in this
yeah, but maybe you have that negative there, so I really know. Yeah, I see what you're saying.
Yeah.
Like, oh, I did mental math and just,
Yeah.
yeah.
Absolutely skip. Just give us the same number that
Just,
we couldn't.
so you should have just went like this. Got it.
Just give us numbers we can't do
put that
mental
little
math.
negative by like 0.
Would you remember?
Absolutely not.
Would you remember the vector over the 0?
Yeah.
Good. Using the property that if u cross v
Vector over the 0?
0 is a unit.
It's cross product.
See, that's why it's being bolded in the note.
is somewhat misleading.
Yeah, because
Yeah.
it's like,
Well, are we going to
That's only that one. The other one you actually have to do.
No,
That one you can just write 0.
The other one with the k, you'd actually show some work, right?
There's no arrows on the.
They're bolded. In textbooks, they're bolded.
Using this way, there's no way to ever
See,
actually show any
this
work.
one
But the
doesn't
other one you'd
have
actually have to do something.
It's not even bolded.
it might try to be italic, but I don't know if an italic zero is like a better question would be like, are these two vectors parallel? And then you have that.
Right, and then you'd have to say, because then you can't just guess that they'll be 0, 0, 0.
Torque? That sounds like physics. We don't do that anymore.
Application of the cross product in physics is torque. That is a tau. That is the symbol.
Tau. But we write it like tau.
It's not a tau.
It is. It is.
Is it supposed to be?
Yeah, it's like it, but we write it like capitalized.
We wrote it an L.
No. L is angular momentum.
What did we write for torque?
Torque is like.
It looks like an F though, yeah, right?
No, it looks like.
Okay, guys, let's just focus on learning. Let's forget about how to write Greek letters.
Like, it's a larger tau. It's not like a tiny tau.
Okay, we have to.
Tiny tau.
Okay, we don't
'Kay.
care.
So your torque is just a cross product of the length of the arm of the object that you have. If you're thinking of a wrench on a bolt, it would be the length of that wrench and the force that you're applying as a vector. And sine of theta, theta is the angle between your force and your wrench. Okay? So for example, if you put a wrench on a bolt and apply a force parallel to the wrench, you just take it right off the bolt. Or even if you use the side of the wrench that has a little round thing so it can't come off the bolt, and you pull as hard as you can on that bolt, will it loosen? No. That would not be. And so you can see that parallel is not a very good choice of applying force to a bolt. Okay, units are the Newton meters. So we have a wrench 15 centimeters long being used to tighten a bolt. Again, think about tightening the same way that you would tighten your toothpaste. a force of 50 newtons is applied to the wrench at an angle of 85 degrees. So let's draw a picture.
That's all I'm doing. To check. Yeah. No, I'll do that first.
There's our wrench. Its length, and since the units are Newton meters, we would measure this length as 0.15. Okay? If we're applying this vector, so I'm going to redraw that vector as vector A. Okay? If we are applying a force to that vector to tighten it, okay, you would be turning it this way just like you would tighten a toothpaste tube. If the angle is applied at 85 degrees, this is the way that you would imagine it, because you would put your hand on the end of your wrench and apply the force there. So we imagine sort of extending this way and imagining that 85 degrees there for our second vector, which is our force vector. Now, when we show the cross product, though, the cross product is always tail to tail. So we take this vector that we just drew and join it tail to tail. So our 85 degrees will be between the two vectors. And this is our force vector. And we know that our force vector is 50 newtons with 85 degrees there.
So what's the first vector?
The first vector is your wrench and the length of your wrench. So you know that the longer the wrench you have, the more torque you're going to have on that bolt, or the less force you're going to need to provide the same amount of torque to that bolt. So now if we want to find the torque, length of A is 0.15, length of B was 50, sine of 85 degrees. .47 Newton meters. Part B to this question, find the magnitude. Oh, we did that. Part B. Oh, yes, we didn't write the direction. Thank you. And this is where I find the wrench example, the toothpaste example, really helps me remember the direction of the cross product. Because in this case, yeah, we're tightening. Thank you. Thank you. I was just about to explain it. I would have realized it as soon as I start to explain it. So if we're tightening the bolt, or if you're tightening a screw, it's going to go down into the wood or down into whatever surface that you're tightening it into.
So into the page.
Into the page.
Surface of
No, you got it that way. See? No, we
but
had
it's
an
down
argument
here.
yesterday.
Oh, he likes
Saying downward.
inwards.
Wrong because this should be.
Because if you were underneath a vehicle doing the same thing, it would be upwards, right? That's what you're saying. So you like inwards
Because in like
as opposed to downwards.
Well, I'm looking down at my page.
And then in part B, thank you, what angle should the force be applied to maximize the torque?
90.
90 degrees.
0 degrees.
Why does that happen? Well, if we look at our formula, the angle that maximizes is when sine is at a maximum. The biggest sine can be is equal to 1, and sine is equal to 1 at 90 degrees. It's like this person is a little bit over. Yeah. And for that person trying to tighten that bolt by pressing parallel with their force and keep trying and keep trying and keep trying. Yeah. Awesome. Okay, I've got some questions for you.